Welcome to another video. Today we're going to talk about exponentials. I know that you've seen them before, you probably heard them before, you might even graphed them, but we're going to look at them under kind of the why they look the way that they do and how we're going to use them for logarithms in just a little bit. So we really want to get a good feel of why these are created the way they are, why they look the way they do, why they are one-to-one functions, and that they will create an inverse graph that we call a logarithm in just a little bit. So deeper than just a cursory understanding of, hey, this is what an exponential looks like. So we'll talk about right now what an exponential is, but that should be in the back of our thoughts as why they look the way that they do. I'm going to create two graphs at the same time. We'll talk about key points, domain, talk about range, horizontal asymptote, and then we'll move on from that. So what an exponential is. An exponential is different from a polynomial. So a polynomial, what it does, it takes a variable and raises it to a constant exponent. It has a lot of different terms. You can do that and adds them all up. An exponential switches that. It takes a constant that we call a base that's always positive and not 1 and not 0, and it takes it to an exponent, which is a variable, which is a very interesting concept. We get a lot of really good population modeling from exponential type of growth. So that's what this means. So when we say a function where we have a base that's a constant raised to a power or an exponent that's a variable, that's an exponential function. A is always positive. It's not 0 and it's not 1 for the following reasons. If you had A having the ability to be a negative, what would happen is we'd have this negative number. Raised to the first power would give you a negative, raised to the second power would give you a positive, and we get this very disjointed, non-continuous graph. We have a lot of discontinuities in that. It'd be very difficult to even graph, really consider what's going on, and so we disallow that. Instead, we say, hey, our base is going to be positive. It's not going to be 1. Why? Why can't it be 1? Well, if you take 1 to any power, you're going to get 1. It's going to create this horizontal line at y equals 1, which would be great if that's all we were doing, say, oh yeah, every exponential is this. But that's not true. What we're going to understand about this is that as our base gets bigger than 1, we're going to get an increasing graph. And as our base gets less than 1, but not negative, remember, it has to be between 0 and 1, basically, we're going to get this decreasing graph, and we will explore that as we continue. So that is what an exponential comes from, is this base that's a constant, that is positive, not 1, raised to this variable that is your exponent, and that's going to be changing. So now we're going to move on to talk about graphs. You see, there's two cases when we talk about exponentials. Even though our A is positive, always 0, we have this 1, this value of 1, that causes our graphs to either always increase or always decrease, depending on whether our base is above or below that. Why? Why is that the case? And this is going to be the fundamental reason why our graphs look different. Here it is. If you take 1 to any power, true enough, you get out 1. If you take numbers that are greater than 1, and you take them to positive exponents, those numbers are going to grow. So if I take numbers like, let's use this for instance, let's use 2 to the x. And I take 2 to the first, I'm going to get out 2, 2 to the second, I'm going to get out 4, 2 to the third, I'm going to get out 8, and then 2 to the fourth, 16. If I take numbers that are more than 1, and I take them to positive exponents, these are going to grow. Numbers greater than 1 raised to powers that are positive are going to grow. Numbers that are less than 1, so between 0 and 1, like fractions, like 1/2. And it does have to be in parentheses, it's the whole fraction being raised to that power. If I take a base of 1/2, or numbers between 0 and 1, and I start taking them to positive exponents, what happens? Well, 1/2 to the first power is 1/2, sure, but 1/2 to the second is 1/4, 1/2 to the third is 1/8, 1/2 to the fourth is 1/16. They get smaller. This is the reason why our graphs do two different things, is because values that are greater than 1 when I take them to positive exponents grow, and values less than 1 when I take them to positive exponents shrink. They decrease. How about negative? Numbers that are greater than 1, when I take them to negative exponents, create reciprocals for us. So that was a concept a long time ago. Negative exponents don't create negative values. They create fractions. or reciprocals of fractions if we start with fractions. So 2 to the negative 1 doesn't create negative 2. It creates 1/2. 2 to the negative 2 doesn't create negative 4. It creates 1/4. And so this is going to climb. And likewise here, 1/2 to the negative 1 doesn't create negative 1/2. It creates 2. This is going to fall, which is the reason why we have these two different graphs. So we're going to explore that right now in a little bit more detail. We're going to come up with the fact that every single exponential has some key points and a horizontal asymptote and why that is. So I talked about some values. We're now going to plot them. We're going to see why this graph climbs. We're going to see why this graph falls. We'll get our key points from that. So let's plug in some values. If we start by plugging in, let's say 0. 0 is always a great value to plug in because it gives us our y-intercept. If I plug in 0, 2 to the 0 power is going to give me 1. How about when I plug in 1? 2 to the first power is going to give me 2. So I'm getting out 0, 1, 1, 2. If I evaluated for 2, I'd get out 4. And we can use a lot more values. If we want to plug in 3, 2 to the third would give us 8. 4 to the fourth would give us 16. 5 to the fifth would give us 32. This is going to be a pretty steeply climbing graph. Now, if I evaluate some negative values, like negative 1, 2 to the negative 1 power, 2 to the negative 1 equals 1 over 2. That's going to be 1/2. And 2 to the negative 2 would give us 1 over 2 squared. Well, that's 1/4. And so we don't climb back like a parabola. We don't get negative. We get these values, positive 1/2 and positive 1/4. Now here's a big question. If I plug in negative 3 in your head, you should be thinking, let's see, 2 to the negative third, that's 1 over 2 cubed, that's 1/8. And then if I plug in negative 4, that'd be 1/16, then 1/32, then 1/64. Is this ever going to hit 0? Is it even possible? Is it even possible to take a value and put it here and make this 0? Is 2 to any power equal to 0? Well, you try 0, right? But 2 to the 0 power is giving you 1, not 0. It's impossible for us to plug in a number here that's going to cause this to be 0. In fact, this is big. It's impossible for us to plug a value in here that even makes this negative. I tried positives, it gave me really big values. I tried 0, it gave me 1. I tried negative, it gave me fractions, 4 bases that are greater than 1. It's just giving me fractions, but they're positive. This has no ability to give me an output that's negative. Now that's interesting. That says that we can plug in any number, right? Our domain is going to be all real numbers. But I can't get out every number. I can't even get out 0. Oh, I can't even get out 0. I can't even get out negatives. And therefore, since I can't get out negatives and I can't get out 0, we're going to have a horizontal asymptote at y equals 0. This graph is always increasing. That is what an exponential looks like. If your a is more than 1, we're going to remove the 2 and talk about in general when a is greater than 1 in just a minute. Before we do that, we're going to answer this graph. So let's take a look at 1/2 to the x. Let's start plugging in some values exactly like we did. If we evaluate 0 and I take 1/2 to the 0 power, so I'm evaluating x equals 0, 1/2 to the 0, anything to the 0 powers, if you have a base that is a positive number, is going to give you out 1. Well, that's the same exact output as here. Now let's ask another question. Is it always true that if I take some sort of constant and I evaluate it for x equals 0, am I always going to get out 1? The answer is yes. Every single one of these exponentials, before you start shifting it, manipulating, do transformations, every one of them, if you evaluate x equals 0, it will give you out 1. Why? Because any constant raised to the 0 power is 1. That's huge. That's going to be a key point for us. Now let's move on. What happens if I plug in 1, evaluate for 1? If I evaluate for 1/2 to the first power, remember that's our variable, 1/2 to the first power is going to give me out 1/2. Anything raised to the first power gives you back what you plugged in. So I get this point 1 comma 1/2. Well, wait, over here, I evaluated 1 and I got out 2. Here I evaluated 1, I got out 1/2. Is it true that every time you evaluate an exponential for the value x equals 1, you'll get back the base? Is that always true? The answer is yes, that's always true. If I plug in 1 here, I'm going to get the base, 2. If I plug in 1 here, I'm going to get the base, 1/2. If I plug in 1 here, I'm going to get the base, a. Those are the two and only two key points you ever need for exponentials in order to graph them, especially with transformations. You need the key points 0, 1, and 1 comma the base. Don't go any further until you understand that those two key points are going to show up on every exponential before we shift it. You need that. You need to understand that with an exponential, if I evaluate for 0, a to the 0 power gives me 1, that's big. And if I evaluate for 1, a to the first power gives me back whatever my base is. These two key points are how we're going to graph in the next video when we talk about transformations. 0, 1, and 1 comma whatever your base is. Well, let's continue. If I plug in 2, well, 1/2 to the second power is going to give me 1/4. Same question as this one. Can we ever get this to touch 0, touch the x-axis, or be negative? Well, if I plug in 3, I'm going to get 1/8, 4, I'm going to get 1/16, 5, I'm going to get 1/32, 6, and so forth and so on. I can't ever make this negative. In fact, if you take a positive number to any exponent, you're not going to get a negative. We explored that here. This can't be negative. It is going to get closer and closer to 0 as an output. Well, wait a second, that's this idea of a horizontal asymptote again. So we have the same idea that both of these graphs and every exponential in general is going to have a horizontal asymptote on the x-axis before you start shifting it. On the x-axis or at y equals 0. Now, what happens when we plug in negatives? If we evaluate for -1, 1/2 to the -1 power, there's a nice property of exponents. It says if you evaluate a fraction to a negative exponent, you can reciprocate the fraction. And it will change the sign of your exponent. So 1/2 to the -1 is equivalent to 2/1 to the first power. That means we're going to get 2. And likewise, if that's a -2, I would reciprocate and have 2/1 squared. Well, that'd give me 4. These functions are in fact symmetrical about that y-axis. We can see that this one is increasing all the time, this one's decreasing all the time. We can see they both have a key point of 0, 1, and 1 comma whatever the base is. Here's your 0, 1, here's your 1 comma your base, here's your 0, 1, and here's your 1 comma whatever your base is. This is true in general for exponentials until you start shifting them around. They both have a horizontal asymptote at y equals 0. That's also true for exponentials. So this is kind of a big deal, understanding where these things came from, why they look the way they do, and especially identifying what they're going to look like for your base. So if your base is more than 1, they're going to increase. If your base is less than 1, they're going to decrease. In general, this is if this a was just greater than 1, not specifically equal to 2, and we started erasing some of this stuff and saying, well, I don't know exactly what my base is. Here's how this graph is going to look. If your a is more than 1, you're still going to get 0, 1, but you'll just have some sort of a key point that's above 0, 1. Why? Well, if a is more than 1, and you plug in, let's say 1 here, you're going to get 1 comma a. If your a is above 1, it will be 1 comma something above 1. It would have to be above that value if a is above 1. If a is below 1, so we'll change this to not necessarily 1/2. If your a is less than 1, then when you plug in 1, you're going to get something 1 comma something less than 1. That's below here. That's why that has to drop. If both of these functions, whether a is above 1 or below 1, if both these functions have that point 0, 1, then the a being greater than 1 would climb, and the a being less than 1 would have to fall. In general, that's true. So here's the way I like to think of it for exponentials. If a were to equal 1, which it's not going to, if a were to equal 1, you would get a horizontal line. 1 to any power is going to give you the horizontal line. That's a constant. If your a is greater than 1, that raises the positive side of your y-axis and lowers the negative side. If a is less than 1, it's reverse. So a more than 1, start climbing. And the more you're more than 1, the steeper it's going to climb. A less than 1, you're going to start falling. The more you're less than 1, you're going to start really falling dramatically. That's a cool thing. One other thing to see here is the, I don't know. No, I'm not going to show it to you, but there's some evenness going on with the switch of a sign. We can get a reflection of these graphs, which is kind of neat to see. This is key. This is what we want to know. This is what we want to talk about. In general, that's true for your key points. That's true for your horizontal asymptote, which we'll explore in the next section. Other than that, our domain for our exponentials, you should see this. You can plug in any number. We plugged in 0, we plugged in positives, we plugged in negatives. There's nothing wrong with this. Your range is not all real numbers. Your domain, you can plug in anything, all real numbers. Your range is strictly positive. You cannot get out 0 and you cannot get out negative numbers from an exponential before you shift it. So your domain is from 0 to positive infinity, but it's not including the 0. That's another way to say all real numbers. Range, we get out things very close to 0, which is why we don't use a bracket, all the way to positive infinity in both of these cases. All right, so the last thing, and a very important thing, we have a special number in math. We have lots of special numbers in math. One of them is pi, one of them is e. Now, I know you're familiar with pi, and hopefully you're familiar with e. This number e right here, that is a constant number. It is a value that does not change. And it's a weird value. It's called the Euler number. Euler is spelled with an E. And so this is based on him, Leonard Euler. It is called the Euler number or the natural number. And it's about 2.7. Now, this number we can't write out as 2.7 because it goes forever and it doesn't repeat. It's a transcendental number, but that is a very special number, and it occurs a lot in nature and in a lot of mathematics. So it's really useful to understand an exponential based on that number e. So e is approximately 2.7, about. 2.71, and it goes forever. And it doesn't repeat for any length of time that's modeled by a fraction. So it's not a fraction. Here's the question. In which of these two graphs would best model that? Would it be a graph that's always increasing or a graph that's always decreasing? Well, let's think about that. What is the base? So is it exponential? Sure, it's got a base. What is the base? Is the base more than 1 or is the base less than 1? If the base is more than 1, it can't look like this one. It's going to look like this one. In fact, it's really close to this. This is going to be, if we did f of x equals e to the x, let's see what these values would do. If I plug in 0, am I still going to get 1? Yeah, always. Every exponential does that. If I evaluate for 0, e to the 0 is still going to give me 1. I'm still going to have that value. If I plug in 1, am I still going to get my base out? Yes, except my base is going to be e. So e to the first power is going to give me e. What that means is that for our graph, we get something that, if this is 1 and this is 2, we get about, I'm going to change this a little bit. Evaluate for 0, we get out 1. Evaluate for 1, we get out 2.7. Roughly 2.7, this would be 1 comma e. And we can see right there that if every exponential has a 0.01 and you evaluate for 1, it gives you out your base. Then if every exponential has 0.1, if your base is more than 1, you'd get out something above 1. And less than 1, you get something less than 1 when you plugged in 1. So evaluate for 1. If a is bigger than 1, it's up here. If a is less than 1, it's between here. That gives you whether it climbs for bases greater than 1 or falls for bases less than 1. It has to do that. So this is going to give us a climbing graph. It's a little bit steeper than 2 to the x, but it's very close because that's 2.7. This is how the graph of f of x equals e to the x looks. It still has those key points. It still has that horizontal asymptote. This is still the domain of range. Is it going to be useful to try to solve for x-intercepts for an exponential? They don't have any. So that would be kind of a waste of time. These are not going to have them until they start shifting down. Can we solve exponentials? Yes, but we need more to it. So I told you the idea behind what exponentials are. I told you why we're going to need them. Here's the key points and the key points. The key points of what you need to remember for exponentials. Number 1, exponentials are caused by taking a base to an exponent that is a variable. Your base has to be positive. If your base is more than 1, your graph is going to climb. And if it's between 0 and 1, your graph is going to fall. This is always increasing. This is always decreasing. They both have the key points 0, 1, because when I take a constant to 0, I get out 1. And they have the point 1 comma whatever your base is, because if I take the base to the first power, I'm going to get it back. They both have a horizontal asymptote at y equals 0. That's always true for exponentials until I start shifting them. Finally, e to the x is a very special case of an exponential where we have a certain base that's used very often in nature, sciences, and mathematics, and that base is e. E is approximately 2.7, and so we are going to get this ever-increasing graph. This is always increasing on the domain, just like that one's always decreasing. And finally, this is like the whole punchline of what logarithms are going to come from. Is this function one-to-one? Use your horizontal line test. Certainly a function. Is it a one-to-one function? Yes, because no outputs are ever repeated. And that's also a one-to-one function because no outputs are ever repeated. Well, if a function is one-to-one, it has to have an inverse. In a couple videos from now, we're going to take that idea and we're going to explore it. We're going to say, yeah, this has an inverse. In fact, we could graph it. It would be not hard to graph. We'll change our key points from exponentials and get key points of the inverse of an exponential. We'll call it a special name called a logarithm, and then we'll discover that they solve each other. So that's very important because right now, there's no way to solve that function if I set this equal to another function or like a constant or something and try to solve it. We really can't do it unless some special cases arise. So that's what I want you to know right now, where they come from and where we're going with it. I hope we explained it well enough for you to understand that. Next time we'll practice it. I know that this, while not being vague, doesn't let us practice very well how to graph these. So we're going to practice next time when we do some transformations of exponential functions. Hope you're doing well.